Hey guys, this video is going to be about modeling exponential growth and decay. So we're going to explore those exponential models. So basically we're running into a new parent function. So an exponential function is a function that can be written in that general form that I've boxed in red. Y equals a times b to the x. And this is where a doesn't equal 0, b is greater than 0, and b does not equal 1. So anything that is in that form, where x is in your exponent, that is an exponential function. Now this y equals ab to the x, the a value is your initial value. That's going to tell you what your y-intercept is. The b value is going to be your growth or decay factor. You're going to know if it's going to be a growth if b is greater than 1. That means your function is going to be increasing. If b is between 0 and 1, you're going to have a decreasing function. Now, either way, whether it's a growth or a decay, your y-intercept is going to be that initial value. So 0a would be a point that you could graph. And you're also going to have an asymptote when you're graphing an exponential function. And an asymptote is a line that a graph approaches as your x value or your y value increases. So in other words, an asymptote is going to be that line where the graph's going to get super close to it, but it's never going to intersect it. So with an exponential function, you'll notice you have this y equals 0 as your horizontal asymptote for both the growth and the decay factor. So let's go ahead and graph some functions. So if I have this f of x equals a third x, and I want to plug in, say, -2. So that is a third raised to the -2 power. Well, that equals 9. If I have a third raised to the -1 power, that is equal to 3. A third to the 0 power is 1. A third to the first power is a third. A third squared is equal to 1/9. So if I graph this and plot -2, 9, -1, 3, 0, 1, notice that's your y-intercept, 1, a third, 2, 1/9. Okay? Now, I'm going to go ahead and let me choose a different color. Let's just go red. I know I'm going to have a horizontal asymptote here at y equals 0. So if I go ahead and graph this, do the best that I can here, my graph is going to hug and get very close to that horizontal asymptote y equals 0, but it's never going to truly touch it. I want you to notice that this graph is a decay. Why is it a decay? Because my growth factor is a third. So notice where I put the arrow, that is my growth factor. And then our initial value is what's out in front, and that would be a 1. Okay, so since that growth value is between 0 and 1, I'm going to have a decay. Okay. Now, let's take a look at g of x, which is 2 times 3 to the x. When I plug in -2 and I take 2 times 3 to the -2, I end up getting 0.22. When I plug in -1, I end up getting 2/3, which is 0.6 repeating. I'll just say 0.66. If I have a 2 times 3 to the 0, well, 3 to the 0 is 1, and 1 times 2 is 2. Notice that's my y-intercept. My y-intercept is 0, 2 because my a value is 2. When I plug in 1, I have 2 times 3 to the first, and that's going to give me a 6. When I plug in a 2, 2 times 3 squared, 3 squared is 9, times 2 is 18. Well, it looks like that 218 I'm not going to be able to graph, but I can graph the rest of this. What I see is this is an exponential function. I'm going to go ahead and graph that horizontal asymptote And let's graph that negative 2.22 and negative 1.66, 0, 2, 1, 6. 218 is going to be off that graph. So notice this is going to be an increasing function. An increasing function is called a growth. This is going to be an exponential growth. Okay, so just by looking at the equation, I should be able to tell if it's a growth. Look at the growth factor. Look at that b value. So if b is greater than 1, it's going to be a growth. If it's between 0 and 1, it's going to be a decay. So let's take a look at some equations here. I want you to identify these just as growth or decay, and I want you to be able to find the y-intercept. Okay, here's what I know. In order to say it's a growth or decay, I look at the b value. Here's the b values, okay? Because if I have that equation, y equals a b to the x, the b value is our growth or decay factor. Let's see. Here, b is 4. Well, that means b is greater than 1. It's a growth. Looking at r of x, well, b is 0.75. That means b is between, it's less than 1, but it's bigger than 0. So it's between 0 and 1. Therefore, it is a decay. All right, so now let's talk y-intercept. The y-intercept is the initial value. Well, if I would plug in 0, 4 to the 0, 1. 1 times 3 is 3. Notice the a value. The y-intercept is 0a. So the y-intercept for r of x, well, that would be 0, 11. Okay, so just by looking at the equation, we can pull out some information. Now let's apply our models of exponential growth or decay. Okay, so here's a model for exponential growth or decay. A of t equals a times the quantity 1 plus r raised to the t. All right, well, here's what I know. Let me get a color here. Let me go with green. This a of t, that represents the amount after t time periods. So the amount after some, amount of time. A represents the initial amount. Initial amount would be the amount you're starting with. Okay. R. This R shows you the rate of growth. Right? And it's going to be a growth if R is going to be greater than 0. And it will be a decay if R is less than 0. So that's the rate of growth, I'll put here, or decay. And then T, well, that represents your number of time periods. All right, so let's apply this. Let's apply this exponential growth or decay model. So this first example, you're going to buy a savings bond. All right, so let me see if I can pull this calculator out here. There we go. All right, so we got this the savings bond for $25 that pays a yearly interest rate of 4.2%. What will it be worth after 15 years? So in other words, I want to know, what is the amount after 15 years, the initial value, $25, 1, well, if it's going to gain interest, that's going to be a growth, so plus 4.2% in a decimal is 0.042, and that's going to be raised to the 15th power. Okay, so here's what I got. 25 times 1.042 raised to the 15th. All right, so let's see here. Let's take a look and plug this in. So I'm going to go 25 and 1.042, and I'll arrow out, and that's going to be raised to the 15th power. And I'm going to push enter. So that's going to be $46.34. So after 15 years, that saving bonds is going to be worth $46.34. Okay? Let's take a look at another example. You invest $30 in a savings account, or $300, not 30, $300 in a savings account that pays 4.5% annual interest. Annual interest, how much you get per year. How many years will it take to grow to at least $500 without depositing or withdrawing any money? Meaning you're not putting any money in and you're not taking any money out. Basically taking this $300, putting it into a savings account, letting it sit and rot until you got $500. Okay? So let's get that equation. A of t, that is the amount after some time period t, equals the initial amount, 300, times 1 plus the rate is 4.5%. Change that to a decimal, 0.045, raised to the t. Okay, so what was the amount that we wanted? Well, we want $500 here, equals 300 times 1.045 raised to the t. Well, we need to find out what t is. Okay, so we're going to use our table function in our calculator to find where the output is about $500. Like, after how many years will I have $500? So under Y1 in your calculator, I need you to put 300 times 1.045 raised to the t. Well, in other words, we're going to use x, but so let me go to y equals, and I'm going to go 300, parentheses, 1.045, raised to the x. All right? So let me change that t to an x. That's what we're going to have. All right. I want to go to the table. Second graph. So I'm looking at the table, and what I want to know is, when is the y value $500? When will it reach $500? So let me go down here a little bit. Let's see here. So I'm looking here, and it looks like at 11 years, let me use my table, I have $486.86. And then at 12 years, I have $508.76. And then at 13 years, I have $531.66. So the question is, when will I have at least $500? Well, I'm going to have at least $500 at year 12. So it's going to take me 12 years, and that's going to be my solution to this problem, okay, using that table of values. All right? All right, one last problem here. So we got the initial value of a car is $30,000, and after 1 year, the value of the car decreases to $20,000. So since it says it's decreasing, that's going to be an exponential decay. It says estimate the value of the car after 5 years. Okay, well, let's see here. I need the equation. So the amount after t years is, well, how much did it initially cost? $30,000. Times, let's see, it's going to be a minus something raised to the t. Well, I need to figure out, what is that rate of decay? I don't know the rate of decay. So let me write that down here. Rate of decay. Well, it decreased to 20,000. So I take 20,000 minus what I started with. So it went down 10,000 out of that 30,000. So in other words, it's a negative a third. Okay, so when I'm plugging that in, minus 1/3, or you can think of a plus a negative a third. Okay, well, I'm going to go ahead and say, well, that's just for easier purposes, 1 minus 0.33 raised to the t. And what is the t? The t is 5 years. I'm going to plug that in to 5 years. So I've got this $30,000 car. After 5 years, it decreases to $20,000. I want to know how much it's worth after that 5 years. So after that first year, it decreases to 20,000, went down 10,000, and I want to know how much is my car worth in 5 years. Well, let's plug this in. Let's go 30,000 parenthesis 1 minus 0.33 raised to the fifth. Your car is worth $4,050.38. So after 5 years, that's how much your car is worth. Hope this helps you with understanding a little bit about modeling exponential growth and decay.